AP Chemistry Stoichiometry Review, the mole. We're going to go into a somewhat different explanation of the mole. So before we do, let's just point out the simple answer. The mole is just a number. The mole is 6.02 times 10 to the 23. A pair is 2, a few is 3, a dozen is 12, a baker's dozen is 13, a ream is 500, etc. The mole is 6 times 10 to the 23rd. But let's take a little deeper look on why this matters and why you might need this number. Long ago, it was postulated that the world is made out of atoms. And originally, they may have conjectured that all those atoms are the same size and the same mass. Well, they're not. Let's consider water, H2O. And there it is correctly bonded. Hydrogen tends to always form one bond, oxygen two. But it would not look like just three spheres attached to each other that are the same size, because look at the difference in size. The oxygen atom is huge. It occupies like 89% of the mass. So that makes a big difference when you're trying to think about the world and how atoms appear. An oxygen atom is 16 times more massive than a hydrogen atom. So if you have 1 gram of hydrogen atoms, you have 6 times 10 to the 23rd atoms of hydrogen. On account of it's so light, you would need 16 grams of oxygen to have the same number of atoms. Now, if you think about it, we're going deeper into the mole. We're talking about molar mass. The mole is just a number, but since it's such a large number, nobody ever would count out that many atoms because you'd never get there. Much easier to mass them out. So the mole is just a number. The usage of the mole is almost always its mass, and that is simply the red number or the average atomic mass on the periodic table. There it is there. That's a mole of hydrogen. That's 4 grams would be a mole of helium. Technically, we are talking about molar mass, but hey, you're going to do it that way, right? If you need a mole of carbon dioxide, you're going to weigh out 44 grams of carbon dioxide. So it is just a number, and that is great. It's a number you will use, but when you actually are in the lab, you're going to use your scale, not your counting. For the synthesis of water, let's take a look at it from the point of view of a synthetic organic chemist. It balances out to 2 to 1 to 2. And let's take a look at what's actually happening. You would not be mixing, 2 grams of hydrogen with 1 gram of oxygen. No. There's your hydrogen atoms, oh so small and light. There's your oxygen atoms, oh so much larger. And chemical reactions are simply a recombination of matter, aren't they? So here it is, turning into H2O. They didn't line up that good. These ones should be right next to it, but I think you get the idea. And as written, 2 moles of hydrogen molecules, those 2 pairs that we had, combined with the 1 mole of oxygen molecules to make 2 moles of water. This is also true on a molecular level. 2 molecules of hydrogen combined with 1 molecule of oxygen. However, if you were to weigh it out, and I think I'm going a little bit beyond the scope of this slide, you would simply weigh out, 4 grams, since each hydrogen molecule is 2 grams per mole, and you need 2 of them. 4 grams of hydrogen would combine with 32 grams of oxygen to make 36 grams of water. So the molar mass is really where it's at. That's how you could actually do it. In our next topic, we'll cover balancing chemical equations.